Alright, today we're going to talk about Riemann sums, excuse me, or a way to measure the area between our axis here and some curve, whether it's a quadratic or a cubic or a fourth power, what have you. Just any function that creates a curve. So what we have here, we're on our Cartesian plane. This is our x-axis, this is our y-axis. And I'm going to put a function in here. Boom, there it is. So what a Riemann sum allows us to do is, if we can measure the area between here, our function curve, and our x-axis, between 2 points on our x-axis, okay? And we are going to call these 2 points that we're going to be measuring between our limits. We're going to be measuring from, for example, -1 to 1, 0 to 2, what have you. This allows us to be able to measure an area, and even though the function kind of disappears up off the screen here, we can still measure that area. Because remember, since this is a function, it just keeps going not only up, but also to the right. It just goes to the right very slowly. But we're not going to do that. We're going to look at probably an area right in here. Okay? And we're going to measure that area. Now, a Riemann sum is based off of what we know. And we know that we can measure the area of a rectangle. So, let me see if I'm going to measure it between points A and B. And I'm going to move A over here and B here. Just keep everything nice and symmetrical. It's a little bit easier to see that way. And there's 2 ways you can actually measure a Riemann sum. You can measure it by what's called the upper sum, or the point at which our rectangle, okay, remember a rectangle we can measure in length, or height times width, however you want to call it, where our rectangle hits the highest point, okay, or we can measure it with the lowest point that it strikes. Now then, excuse me, as you can tell, measuring by the upper sum is going to be greatly overestimated, greatly overmeasured, because I'm going to say almost a good 50% of our rectangle is above our function. And then if we go with the lower sum, we're going to be missing this little bit here and this little bit here, so it's kind of an underestimation or an undermeasurement. Okay? Now then, we're going to go back to our upper sums because it's a little bit easier to see. You can see here that this shape, this rectangle, just doesn't really fit our curve very well. Now then, what if I increase the number of rectangles? That should be a little bit more accurate. So I'm going to use a little slider here, and I'm going to increase our rectangle, our number of rectangles between our 2 points to, see if I can hit an even number here. Well, that's almost 5. It's actually measured 4.95, but 1, 2, 3, 4, 5. Now notice, our measure of our different heights here gets a heck of a lot closer to the shape of our curve, making the areas that we're going to measure, this rectangle plus the area of this rectangle plus the area of this rectangle, so on and so forth, a lot more accurate to this area under our curve. The same thing goes with the lower sum. Okay, you can see that it more accurately fits our curve. Let's increase it a little bit more, and you can see it start to fit even more. Isn't that cool? Wow, that's cool. So the more rectangles we have, the more it fits the shape of our function. All the way to the point where, believe it or not, I've got 100 rectangles between A and B. Okay, now I'm going to take it back here to something that we can see a little bit better. Now let's superimpose our upper sum on it. You can see there's a difference between our upper sum and our lower sum. The more rectangles we have, the less that this distance is. So the more rectangles we have, the more accurate we become in the difference between said upper sum and lower sum, which means we get a more accurate measure. So when you integrate a function, what you're doing is you're using the function, and you're going to have a lower limit here and an upper limit here, and that's those two limits are the only things that you're going to be measuring between. You're not measuring way out here, because after a while that just gets, unbelievably difficult, and you're not measuring way out here. We're not measuring the entire area, just on this little section right here. For some reason that may be of interest to us. Excuse me. Okay, so I'm going to turn that off. This is the area of our upper sum. Remember, the upper sums, the rectangles stop at the highest point that they touch. Okay? Notice on the left-hand side of the y-axis is going to be the upper left-hand corners of the rectangles, and on the right-hand side of the y-axis is going to be the upper right-hand corners of our little rectangles. All of that added together gives us this number right here. Now then, all of this number, all of our, let me turn that off. There we go. And here it is for our lower sum. And you'll notice that there's a difference between these two numbers. Just turn that on, turn that on, turn that on. Okay? There's going to be a difference between our two numbers. Now, if you do the math here, you can see that this is accurate. So, notice how when I increase the number of rectangles, the distance goes down, meaning that we're becoming more and more accurate in the area that we're supposed to be measuring. Down to the point, 0.04. That's pretty darn accurate. The idea behind integration is to get excuse me, the number of rectangles that we're going to measure. I'm going to turn that one off. The number of rectangles between our two bounds, our two limits of integration here, we want that to reach infinity. That way we have these infinitesimally thin rectangles that we're measuring, or using to measure. And of course, still, again, we're using our width and our height to measure the area of these little rectangles. So, you can't see it here, and I don't think I can drag it out. I might be able to scoot it over a little bit. No, unfortunately, the camera is just not positioned in a way that's... Oh, yeah, here we go. And let's see. Okay, difference of the sum. Okay, so I've got everything turned on except we're only looking at the lower limits, the lower sums here, and I want you to watch something. I don't know what happened there. Oh, that's what happened. Okay. Notice the difference here. Huge difference. Not even close to our integral. The more rectangles I hold, the integral doesn't necessarily change, but we start becoming more and more close, see here and here, to the actual measure of that area when we start adding in rectangles. To the point that I can get to 0.02 units within it. So that's pretty cool. What does this one do? I don't know what that one is. Okay. So yeah, there you go. And let's see something else here. I'm going to turn that on so you guys can see the upper sum also. Excuse me. What does the upper sums measure do as we start adding rectangles? Notice how it is going down to our actual integral, and the lower sum is going up to it. So our integral, our measure of the actual area, is right in between our upper sum, which is an overestimation, and our lower sum, which is an underestimation. So I hope this explains Riemann sums just a little bit more for you, so you can kind of see how they work. That is just so cool, isn't it? I'm going to move this back over here, that way you guys can see. There we go. Pretty neat, huh? Huh. Let's see if it does it all by itself. Yep, there we go. Notice how our differences get smaller, and so does the difference here. And both of our values become closer and closer to the actual measure of the integral. Okay, I hope that explains things for you guys. Have a good night.